now let's see dominant strategies in the prisoner's dilemma. So different ways to write down the prisoner's dilemma. The prisoner's dilemma is the most famous game in game theory, and the prisoner's dilemma has the following story. The story is there are two prisoners. They're caught by the police. They are kept in two different prison cells. They cannot communicate with each other, and the police tells them, okay, we can either cooperate and confess, or we will not confess. You can also can confess or not. And if both of them do not confess, and because they have committed some minor crimes, they go to prison for 2 years each. If one of them doesn't confess, but the other does confess, so one does not confess, two confesses, the guy who's not confessing is incriminated by the other guy, and the guy who doesn't confess gets 10 years in prison, and the second guy only 1, so it's less than the 2 if both of them do not confess, but much better than the -10, although -2, so it's the best you can get. If prisoner 1 is the one confessing, the prisoner is 2 not, so it's -1, -10, so 1 is one getting this bonus. And if both confess, and if both confess, they also get -5 years. 5 years in prison. So if you solve this game, you will see that if prisoner 2 does not confess, prisoner 1 should confess. And if prisoner 2 confesses, also prisoner 1 should confess. Because it's symmetric, the same for the player 2. If 1 chooses BC, C is the best reply for player 2. If prisoner 1 chooses C, C is the best reply for prisoner 2. Both prisoners, independently of what the other guy does, will choose to confess, and you solve the game in dominant strategies. This is called, if you don't have an optimal strategy independently of what the other guy does or can do, this is a dominant strategy. There's a dominance versus strategies. It's always a best reply. And the dominated strategy is easy, it's never a best reply. And then you see the outcome is in Nash equilibrium, most players confess and get -5. And the funny thing is, or the thing which is perturbing at the beginning at least, is that if both of them choose DC, they go to prison for 2 years only, so it's much better for them jointly choose DC and not CC. But if they choose DC, both of them or one of them, the other has an incentive to choose C, and you get the lowest prison sentence. So DC is strictly dominated for each player, so it yields a lower payoff regardless of the other player's strategy. And C is strictly dominant, so strictly means it gives a strictly larger or lower payoff in this case. Strictly dominated means strictly lower payoff. Strictly dominant, it gives a strictly larger payoff, and this is the Nash equilibrium of the dominated strategy, CC. You only require rationality, but not common knowledge of rationality, because I solve the game for me, I don't care what the other guy does, I know I play C, so if the guy chooses DC, I don't care. No common knowledge necessary. So from this we learn, players will not choose dominated strategies, so we can remove the dominated strategies from the choice sets. As we delete strategies, as I said, it might become dominated in a very similar strategy as well, but we only can delete strictly dominated strategies. If a strategy is only weakly dominated, because it sometimes gives you strictly more, and sometimes the same, you cannot eliminate it, because then it depends on the order in which you eliminate it, and it's the outcome. Now, let's start with this. This again with 2 players. We want to up and down, there are 2 left and right. After brief inspection of the payoff matrix, we will see 1, if you choose middle, gets always 0. And if you choose either up, it gets 1 to 1, or down to 1, 2, it gets strictly more. You never choose middle. We eliminate middle. Once you've eliminated middle, now for player 2, check the payoff of player 2. Here it gets 1, 1, here 0, 0, here 1, 2. So now center is strictly dominated for player 2. Here you would still choose center, but once we eliminated player 1's middle, here, so 1 is not in 0, 0. Once we eliminated it, now you always get 0 when choosing center. And you can eliminate this, because now player 1 is better off to choose down than up, and then player 2 choose right and not left. And then by the elimination of strictly dominated strategies, we get to the unique Nash equilibrium. You can only also get to the Nash equilibrium by underlining these best replies. You also get to the same outcome. So there are 2 ways to get to this. Sometimes you cannot start, because here what happens is, now I put a 1 here and the 0 and the up down, so here up is better than middle or down, here middle is better than center or down, here right is better than, right is, up is worse than middle than down, and so what we can do is, now I draw it. If player 2 chooses left, player 1 chooses up, you choose center, you choose right, say you choose middle, you down. If player 1 chooses up, player 2 chooses right, here chooses center, and here chooses left. Okay, so you see for each player, you have here B is the best reply, here M, here U. Here R is a best reply, here C, here L. So as long as a strategy is used as a best reply against some strategy of another player, you cannot eliminate it. For most players this is true, so you cannot start iterative deletion of strictly dominated strategies. And you see the Nash equilibrium is the one where both are 9 and C. Okay. And strategy SI is the best response. Well, if you get a larger payoff, as we had before with the Nash equilibrium definition with the stars, then it's the best response if you get a larger payoff. That's what we just did here. Now, Nash equilibrium is if it's basically as we already had before. So it's a Nash equilibrium for every player. As the strategy SI is better than any other strategy, or at least as good as any other strategy, or any strategies that you can choose. When there's no unilateral profit elimination, this is the same definition as before. The players, so what's the idea of the Nash equilibrium? The players unilaterally choose an action, and in reality, this either leads to a Nash equilibrium or not. In a Nash equilibrium, if it leads to a Nash equilibrium, no player can profitably deviate. So there's no incentive for any player to deviate and get something better. If we are not in a Nash equilibrium situation, choose another strategy and another outcome here, at least one or both players have an incentive to deviate. Choose UR. UR, player 2 is happy because it's the best reply, but player 1 is not. Against R, the best reply of player 1 is D. You would switch to D. DR, player 2 is not happy. Against D, he would choose L. Like this, you move around until you reach MC. If you reach MC, no player can deviate profit. You can also start with UC. Both players want to switch. And this C, player 1 goes to M, player 2 goes to R. Sometimes both players can switch. And the dominant strategy will then always be part of the Nash equilibrium. Dominated or never best response strategies are never part of the Nash equilibrium. Which makes sense. Then let's consider this game. You can align the best replies. And if you do this, player 1 looks like this. A3 is better against B1, A2 against B2, A1 against B3, and A4 against B4. Then you do the other player. A1, best reply is B1, A2, it's B2, A3 is B3, here's A4 is 2, which is B1 or B3, and you get one Nash equilibrium, which is A2, B2. Which makes it get more complicated. This always leads to an easy way, easy procedure to the Nash equilibrium. Okay, so this was a Nash equilibrium, and here you get also a unique Nash equilibrium. Unique means there's only one. If there are multiple Nash equilibria, which we will see here, we don't know what the players play. We can coordinate to left or right to both Nash equilibria, but we don't know. Left it's a Nash equilibrium or right. If they choose anything which is not matching, so one player left as a right, both have an incentive to change. Which of these two will be played, we cannot predict. We know only there are two Nash equilibria, Once you observe what the players do, you can tell it's a Nash equilibrium or not, but you cannot tell which of them will be. Here, it's quite reasonable to predict that they will lay A2, B2. Here in this case, it's quite reasonable to predict that they MC. But here, no. And so it's a coordination game, you use a coordinator 1 or another equilibrium. Now, we have another coordination game. Says the same equilibrium, but I've made a larger player from the left than from the right. So now it's more likely that the players will coordinate with the left. Because they see, so two equilibria are analyzing the game, but in one we get much higher payoff. So we possibly coordinate with the one that has a much higher payoff. But the description of the game doesn't tell us. The description of the game only tells us that right, if they coordinate on right, it's a Nash equilibrium. Also to get improve unilaterally by changing what you do, left is. So we cannot tell it unless we use additional criteria, like say probably value larger or more, or we cannot say anything else about what to do. Next one, Plaza Maker. Well, here's the story is, many of these games are from the 60s, 70s, and last century, was invented these type of games. Two guys, they don't have cell phones or anything to coordinate or communicate, so he's going into metro to the central square, and they don't know yet whether they meet upstairs at the plaza or they meet downstairs at the metro. So two things they meet likely. Where do you meet? Well, two equilibria, they both meet at the metro, or they both meet at the plaza, but we don't know which one. And in those, again, this is a coordination. And now I show you for this, the third equilibrium. So if there are two pure strategy equilibriums, there's also a third one, mixed strategy. I'll show you now for this. What is the idea of mixed strategy? So mixed strategy is something with probabilities, where you don't play a pure strategy for sure, but you mix between two different strategies. And this is something which happens in the following way. So when you are sitting in the metro, you're going to the central square, you're entertaining your head, you're thinking about the possibilities what to do. You stay either downstairs at the metro, wait for the other guy, and meet or not, or you go upstairs to the plaza. You have to make the decision. But as long as you do not have taken the decision yet, you can think about both options in your head. And this is what is a mixed strategy. Probabilities before you take a decision, the probabilities with which you play each of these two. What's the Nash equilibrium mixed strategies? Well, the idea is basically you have to make the other guy different between plaza and metro, that he can choose anything, he gets the same payoff. And if he also makes you different, you are different, then you play it also plaza or metro, you don't care. There's a certain probability, then you have a Nash equilibrium. If the other guy is not indifferent, because for whatever reason, the way you choose to mix strategies, probabilities, it's better for him to go to the plaza or to the metro, he would go to the plaza or to the metro because he would best reply. Only if he's indifferent, he will mix between the two, he will play the probability. If he's not indifferent, he will choose one of the two because one of the two is better. So this is the first thing. Makes the other player different between plaza and metro. What we said he's willing to play the mixed strategy. If you were not indifferent, he'd be better off to play one pure strategy. So we'll put the P1 minus B in player 2's mixed strategy. P chooses plaza. This probability P. And this corresponding probability 1 minus P. And player 2 will choose mid. Player 2 makes player 1 indifferent. So how does player 2 make player 1 indifferent? Player 1 should get the same payoff, choosing plaza, against the mixed strategy of player 2. Then if player 1 chooses metro, against the mixed strategy of player 2. What's the payoff of player 1 when he chooses plaza, in case player 2 uses the mixed strategy? Plaza gives 3 times P. 3 is the payoff here. And this chosen is probably P, so it's ending up here is probably P times 3 plus 0 times 1 minus P. I don't try to talk. If you choose metro, the payoff is 0. Here, 0P plus 1 minus P. Because this is probably 1 minus P, we have to choose metro. How do we make player 1 indifferent? Well, we make player 1 indifferent is the probabilities are the go to the plaza, we call it 1 quarter. If you do the metro, it's already 3 quarter. Layer 1 is the difference between plaza and metro. And P, so the probability on the one where layer 1 gets a higher payoff, has to be smaller probability. And the one where layer 1 gets a large, the smaller payoff 1, you have to put a larger probability, because only then you can make layer 1 a different. If you put a larger probability on plazas and on metro, and you have a larger payoff for plazas and for metro, then layer 1 goes for the plaza for sure. The other way around is the payoff. Then is P. Q for player 2, player 1 chooses Q. Q. Chooses plaza to make player 2 indifferent. Q. To make player 2 indifferent. No question.
So at any point that is not 1/4, it will be pure strategy, right?
Yes. If P is strictly larger or strictly smaller than 1/4, player 1 would apply with a question. And you can think about it. So if P is larger than 1/4, then plaza is a bit more likely, so player 1 will go to the plaza. If P is strictly smaller than 1/4, metro is a bit more likely, and player 1 will go to the metro. Now the Q. Similar but not the same. So Q you see here. So player 2 chooses plaza against Q, Q2, Q plaza is equal to 3 times Q plus 0 minus Q. And Q2, Q metro is equal to 1 minus Q. And so you get, because it's the same, you get Q is equal to 1/4. It's actually the same here because it's a matrix. So this is the mixed strategy Nash equilibrium. Formally you write it down. The Nash equilibrium you would write down. The sign of Nash equilibrium is plaza plaza, metro metro, because it's always actions they choose. And the mixed one is player 1 chooses with probability mu1. So this is the mixed strategy, this is a sigma. Sigma 1 of plaza is 1/4, so it knows that sigma 2 is 3/4, and sigma 2 of plaza is also 1/4, and it knows that sigma 2 is 3/4. Okay? So this is a mixed strategy Nash equilibrium. This is the set of all the Nash equilibrium. Now how does it work? So the idea is you are sitting in the metro with 1/4, you are going to the plaza with 3/4, you stay downstairs in the metro. Both players do this. This is a strategy, mixed strategy Nash equilibrium. This mixed strategy Nash equilibrium exists as long as you're still in the metro. Once the metro stops at 7 square, you get out of the metro, you have to decide what to do. So the mixed strategy is like an ex ante Nash equilibrium. Once you reach the point of decision, you have to decide. You cannot do both anymore. Here you can think about the two things. You don't know what to do, so you do one, you do another. But once you have to decide, you have to choose between the two. And then it becomes a pure strategy. It's a plaza. So in some sense, many decisions which we take, very often you will for sure have this feeling sometimes, or you will, if I describe the situation, you will remember some situations you had in your life, you're not sure what to do. There are different things you can do, you know about, that certain things might you know, some are better than the others, you're not sure, you have these things in your mind, you're thinking about what to do. Different possibilities. How do you decide? Well, you have a mixed strategy Nash. You wait until at some point in time you have to decide, then you have to decide, and you cannot do both things, and you have to do one of the two things or three things, then it becomes a pure strategy. This is a mixed strategy. The nice thing which you learn from game theory is basically before there's a point of decision, the metro reaches 7 square station, you get out of the metro, you have to take the decision. Until then you can wait. And here you don't get, in this game, there's no new information that arrives, but you reach this point, you get out of the metro, and then you have to decide. But in reality, frequently you get new information. So by waiting, taking time, maybe sometimes you get new information, you're thinking about what to do, and sometimes you find what's a solution. So one of these things, especially if you're younger, I experienced this myself, I'm getting older, I'm usually waiting more with certain decisions. because sometimes the decisions, if you don't know what to do, over time, before you actually have the time limit, or it's basically too late to decide, before this time happens, the decision point comes, there's more new information arriving, or you make up your mind and it's clear what to do. Sometimes it's better than to wait until you have new information, until you made up your mind, and you think about the situation, and then you take the decision. Okay? This is like the mixed strategy. Let's do another game. This is the Battle of Sexes, again from the 70s of the last century. Nowadays nobody would call this the Battle of Sexes. Find a different name with different types of things to do. One of my colleagues, young colleagues in Austrian professors in Germany, he told me this would be the Oppenheimer Barbie game. Instead of having football and opera, you have two friends which decide on going to Oppenheimer or to Barbie. One likes Oppenheimer better, the other Barbie, and the question is to go together to one of the two or not. Okay, so this would be the modern version of the Battle of Sexes. Classic one is you have a cardboard and in a woman, which decide what to do in the evening. It's the 60s, 70s, so they're both sitting in the office working, so they talk to each other. They have to decide to go to the opera or to the football. Independently, you decide what to do. You either meet there or not. If you meet there, both of you, you're happy, because at least you meet the other person, independently of the. If you don't meet, one goes to the football, the other to the opera, or vice versa, both get 0. But if you go both to the opera, player 1 gets 3, player 2 1. In the football, player 1 gets 1 and player 2 gets 3. So you can, the tradition would be from the 70s, that player 1 is a woman, player 2 is a man. Nowadays it might be different. Anyway, so you have these two people which meet, either so you go together to one event, opera, or to the football. If they meet, player 1 in the opera, player 1 gets 3, player 2 1. In the football, player 1 gets 1, player 2 3. But if they do not meet, well, they get 0. And this is like the asymmetric game, operation game, but with asymmetric payoffs. Here's a payoff with a line. So both of us enjoy meeting at the plaza more than at the metro, which might make us go to the plaza. But here it's not. So what do we do? What does a Nash do? Well, optimal decisions. In pure strategies, you have both choose opera, or football. What in mixed strategies? Well, we do the same analysis as before. With the P's and the Q's. Well, let's see. Mixed strategy. So player 2 uses P on opera. This probably choose opera is probably P. So let's put it correct. Choose opera with probability P to make, and this I don't write down, to make the one different between opera and football. What's the pair of player 1? Opera gets the probability of the 2 P, 3 P, and in the 1 football, against the mixed strategy of player 2, it's 1 minus 2. Calculated, it's the same as before. It was 3P, it's 1 minus P, 4P is 1, P is 1 quarter. Player 2 chooses, is probably 1 quarter to go to the opera, which is a higher pair for player 1, so it's lower probability of opera, and with 3 quarter to go to the football, which is actually nice because he has a higher probability of the events that he likes better. Player 1 chooses opera with probability Q to make player 2 indifferent. What's the probability of player 2? Q makes player 1, opera, Q, football. This is Q, and this is 3 minus 2. And now, since the game is not symmetric, we get here a slightly different pair. Sorry, Q1 minus 2. 3 times 1 minus 2. Okay, 3, we have 3 minus 3Q. 4Q is 3, and this gives me Q is 3 quarter. So now player 1 chooses opera with only 3 quarter, and player 2 is 1 quarter, and this is a Nash equilibrium mixed range. And now for this game, what I will do is, if you have any questions, you interrupt me, but I think it's pretty straightforward. It's basic stuff. So in the undergrad, I take only a couple of weeks to teach this stuff, but in the master, I take 1.5 hours. let's draw the best reply picture to see how it looks like with the best replies and when people switch if you're not indifferent, and what are the fixed points. So here we have the space, the PQ space. This is from 0 to 1. The question is, which strategy do you choose? So the first thing we see is if P is equal to 1 and Q is equal to 1, we are here. Both players, if P is 1 and Q is 1, choose opera. So this corresponds to the opera Nash equilibrium. If P is 0 and Q is 0, we are here. We have the second Nash equilibrium, football. We also choose football. P is 0. Player 1 chooses, player 2 chooses football. Q is 0. Player 1 chooses football. Both choose football. So what happens in between? At P is equal to 1/4. It's a mixed strategy of player 2. P is 1/4. This is a P that player 2 chooses to make player 1 indifferent. At P is equal to 1/4, player 1 is indifferent and gets the same payoff independently of what he does, he or she does. So this is player 1's best reply, because at 1/4, any Q is the best reply. Okay, again. Player 2 chooses a P, 1/4, to make player 1 indifferent. So at P is equal to 1/4, player 1's best reply is any Q. He gets the same payoff choosing opera or football or any probability of the two, because player 2 chooses P to make player 1 indifferent. So anything is good. If P is slightly larger than 1/4, so it's a bit more likely to go to the opera, what should player 1 do? Opera. Q is equal to Q is equal. If P is slightly smaller, that's a bit more likely than this 1/4, than this 3/4 to go to the football. Then player 1 switches to football and Q is 0. So this is the best reply of player 1, which is determined by the mixed strategy of player 2. P is 1/4, anything goes for player 1, this is the best reply for player 1. Then we draw the Q. Q is equal to 3/4. So Q is here 3/4. This is the probability with which player 1 chooses opera to make player 2 indifferent. And at the 3/4, player 2 is indifferent. Any P is the best reply. If it's slightly larger, then P is 1. P 1. And if it's smaller than 3/4, P is 0. So this is the best reply of player 2. And then you see nicely. So the fixed point is that the two best replies intersect here, here, and here, and this is where we get the Nash equilibrium. So this is this idea of the fixed point theorem. The best replies intersect. Fixed point means the best replies are the same. At this point, they coincide, they cross, they intersect. So this is where we get the Nash equilibrium. Everywhere where they intersect.
Which one is the best reply for player 2 here?
This is player 2's best reply.
All the line.
Yeah, all the line from 0 to 1 with this at Q equals 3/4 continuous, and this is the one for player 1. And again, I don't have chocks with color, I'm sorry. I missed something I lost. Okay, so this is mixed strategy. This is the best reply picture.
And you said in Nash will be like those 3 points, right?
Exactly. Pure strategy, Nash equilibrium, mixed strategy, Nash equilibrium. This is for the undergrad, this is the most difficult question. For you, this is easy now.
This is the easier question in the exam.
Exactly. I thought this is the easy question.
Sì.
Yes?
Yes.
Now it's easy. Okay, so let's keep going. There are some other types of games I showed to you. One is a chicken game, anti-coordination game. And this is the thing, the idea is two cars are going towards each other. So if they don't swerve, they both go straight. They hit each other and they get a car accident, both get -10 as an outcome. You can also swerve. If you swerve, There are two swerves, player 1 goes straight, he's the one who's not seeding, he gets 1, and the guy loses. Same thing the other way around, player 1 swerves, player 2 doesn't swerve, and both swerves 0, 0, so both swerves. And sometimes the idea is if you swerve, you're a chicken, the loser is the chicken, this is why it's called chicken game. So if both swerves, they're both chickens, otherwise one who swerves is the chicken, and if both go straight, there are no chickens, but if the car accident, then both get -10. What are the mesh equilibria? Well, it is like a resource that is rivalrous but non-excludable, so one of them can only have it, but I cannot exclude the other from using it as well. If the other uses it as well, we have a huge negative externality. You have two Nash equilibria in pure strategies, and then you have the mixed strategy equilibrium. The mixed one I don't calculate, but this is up to you. Calculate it and draw a picture if you want to. The interesting thing is in this space here, since here we had the equilibrium on the upper left and lower right corner. Here we have it here. So in this best line pictures, the pure strategy Nash equilibrium would be here and here. Okay? One guy chooses 0, the other 1. One guy chooses 0, the other 1. Here, this guy chooses 1, this guy 0 probability. Here 1, and this guy. So this 1 and this 0. Okay? So this one corresponds where Q is equal to 0 and P is equal to 1, Q0, P1, and this corresponds to P0 and Q1. Okay, so they're in different forms. This is a zero-sum game, which is a matching penny game, which we analyzed at the beginning. You can also calculate, there's no pure strategy equilibrium, but there is one in mixed strategies. And this you can calculate, and it's both of them with probability 1/2, choosing left and right, or head and tails. This is a mixed strategy matching game. Here are a couple of things. The first thing is, this is a zero-sum game because the sum of payoffs is always 0, so the one player gains, the other loses, and vice versa. And in these zero-sum games, well, they are particular games. On aggregate, there's no winner because the sum of payoffs is always 0. The second thing is, and this you can see from football, soccer, from tennis as well, where you put your, what is it, the first serve or the second serve. Actually, especially in football, the story is shooters are usually having a strong leg, left or right. So they prefer to shoot with a strong leg, with a strong foot, but the goalkeepers know this. So they always shoot with your left leg, left foot, because this is a strong one. Then the goalkeeper knows that you shoot left and he jumps there and he catches the ball. So what you have to do is, even if you're good with one foot, you have to shoot sometimes with the other one in order to get as close as possible to 1/2, that the goalkeeper doesn't know with which probability you prefer to shoot in which direction. If he knows with 2/3 probability you shoot in one direction, you will jump in this direction, and it's more likely for him to get the ball. All the good goalkeepers in the top leagues, national goalkeepers, they all have in their minds, they know before a game, they look at the statistics of the possible shooters, with which probability they shoot in which direction, how this evolves over time, so they know a bit where to jump. And this is why very good goalkeepers very often can stop penalties because they have these probabilities in their head. And the same thing is with tennis, with serving. So the good tennis players will put their serves always 1/2, to the left, right, to the middle, so they will always mix. Bad ones always go in one direction because they know how to do it in one direction well and in the other not. And again, if you play against some other player, the good players, as part of the preparation of the match, they analyze where the other guy is serving, which part of the field. So then you get one equilibrium, only one Nash equilibrium mixed actions. This gives you the Nazi symbol as best replies. So you can try to draw it as well. The interesting thing is, in general, how many Nash equilibria there are. So we've always seen, here we have 2 in pure strategies, 1 mixed. 2 in pure, 1 mixed. 2 in pure, 1 mixed. Here we have 2 in pure, so there's 1 mixed. Same here, here 1. Here we had 1. Then we had the Brisnow's dilemmas, and was 1 in pure strategies. So we have 1 or 3. In the mixed, in the matching pennies, in this zero-sum game, we have 1 in mixed strategies. So we have only 1, 3. And so in general, because of this best reply pictures, the best replies have to cut an odd number of times. They cannot cut an even number of times. So you always have 1 Nash equilibrium, or 3, or 5, or 7, or 9. So the number of Nash equilibria is always odd. And this is both pure and mixed strategy equilibrium. So if you find 2 pure strategy equilibriums, there's 1 in mixed. If you have 4 pure, there's 1 in mixed. If you have 3 pure, there's no in mixed. Okay? 1 pure, done. And this is the number of Nash equilibrium. This is, so sometimes you don't have a pure strategy Nash equilibrium, which always happens in zero-sum games. This is the number of this odd, as I explained to you here. This is a corollary of the fixed point theorem, so they cannot cut an even number of times. Good. Okay, let's start with this second topic. Because the next one. Yeah, there's not many slides. Dynamic games. So what are dynamic games? Simultaneous move games is we take simultaneous decision, it's an equilibrium or not. Sequential games or dynamic games will be that we take a decision, but one of us moves first, and then the other one decides. And we will have different situations, either there's a first mover advantage or a second mover advantage. So let's suppose the same matching penny game, but let's make it sequential. Doesn't make much sense because what happens here? Player 1 chooses first between red and king. So now what we do is we depict this in this way. So decision nodes, player 1 decides here, here, player 2 decides here or here. But these are different decision nodes for player 2 because player 2 observes what player 1 does. After player 1 chooses H, player 2 can decide between H or T. Or if player 1 chooses T, also player 2 can decide between head and tails. So it's an extensive form game where player 1 chooses first and player 2. Since both have 2 actions, for player 2 we depict the 2 possibilities. After choosing, he observes what player 1 does and then chooses. At the end, player 2 chooses also between H and T, and these are the payoffs again. So if the pennies match, player 1 gets a penny, and if not, player 2 gets a penny. What's the outcome of this game? Well, clearly, if player 1 moves first, chooses H or T, this is like first the goalkeeper jumps and you shoot in the other direction. So you always win as player 2, because you observe what player 1 does, you take the penny by not matching the penny of player 1, you take the penny. Player 1 doesn't want to play this game. But how do we find it? Okay, so let's see. First thing is, player 1 has 2 strategies, H or T. Player 2 has actually 4 strategies, namely, here he can choose H or T, and here, so he can choose HH, HT, TH, and TT. So it's H if player 1 chose H if player 1 chose T, H if player 1 chose H, and T if player 1 chose T, T if player 1 chose H if player 1 chose T, or T if H, T if H, T if T, sorry. So in some sense, player 2 has more strategies here, so it's not identical to the game we saw before, because player 2 has more strategies, because he can condition his strategy on player 1's choice. And in the equilibrium, he has to tell for each possible choice of player 1 what he would do. So he has to say what he would do after player 1 chose H, and after what player 2 would do after player 1 chose T. This was a simultaneous move game. But this game, so if we can write down this game also as a simultaneous, as a normal form game. If we write it down as a normal form game, we have to take into account that player 1 has, so player 1 has 2 strategies, and player 2 has 4 strategies, okay? So this one is a normal form game corresponding to this extensive form game, and let's fill it in to see how it looks like. Because in some sense, if you convert it in this game, again they choose simultaneously, so player 2 has to decide what he does for every choice of player 1, and player 1 can choose between the 2, so you have the 4 possibilities for player 2. If it's HH and H, player 1 chooses H here, player 2 flips the payoffs again, so player 2 score minus 1, player 2 gets minus 1, and so this is the first payoff, this is player 2's payoff, this is player 1, and this got 1. If he chooses T, because they do not match, like this. HT, H here, again, minus 1, 1, because they do match, and TT, they also match, minus 1, 1. TH, here they do not match, 1 minus 1, here they do not match, T 1 minus 1. TT, here they do not match, and TT, they match, minus 1, 1. Okay, so you would have to fill it in like this. This would be the normal form game corresponding to this extensive form game. So how can we capture this game? We can capture it when we solve it. So the interesting thing is this game here, it's a sequential version, but since it's not identical to this normal form game. So this extensive form game gives us this normal form game here on the board. How can we capture this game here? This normal form in extensive. How we capture it? In this way. So what we need to do is that player 2 has only one possible strategy. He cannot observe what player 1 does, whether he chooses H or T, but he only observes player 1 has chosen. Now player 2 has to choose, but he doesn't know whether player 1 chooses H or T. And then player 2 has only one choice, which is H or T, and we are back in this game. Okay? So this is a normal form game corresponding to this game. So if you connect with this red dotted circle, the two decision nodes of player 2, then he doesn't know the information what player 1 did before him, and they are connected, so he has to take one decision in both cases. And then we are back here. Good. Let's do another one. Entry game, two players, entrant and incumbent. The entrant chooses to enter or not. The incumbent can fight or combo. So the outcomes will be out fight. So player 1, the entrant chooses out. And the incumbent either fights or accommodates. Or the entrant enters, enter fight, and enter accommodate. And the incumbent fights or accommodates. The payoffs will be the following ones. So in an extensive form game, it looks like this. If the entrant chooses out, he gets 0, the incumbent 2. If the entrant enters, the incumbent will fight, minus 1 for the incumbent, minus 3 for the entrant. And if the incumbent accommodates, the incumbent gets 1 and the entrant 2. Then you can see that there are two Nash equilibria. One you can easily find, and this is what I show you. So what we did here implicitly, we solved the game from the end. We were checking what is the best decision of the second player when he moves, the last player moves. Here he compares these payoffs. T is better than H. Here H is better than T. Then player 1 chooses, doesn't matter because he always loses. Here we start at the end again. What is the best decision of the incumbent? He chooses accommodate. Better than fight because 1 is better than minus 1. Given this, so this one will not be chosen. The entrant decides between out giving 0 or in, anticipating that the incumbent accommodates, gets 2, so the entrant will choose in. This will be one Nash equilibrium, and we also can find this by this looking backwards, which is backward induction. It's called starting at the end of the game tree, analyzing what the last player does, and going upwards. But there's another Nash equilibrium, which is for the entrant to choose out and for the incumbent to fight. The entrant chooses out, the incumbent fights. Is it a Nash equilibrium? Well, we know if the entrant enters, the incumbent would accommodate because entrant in, the incumbent accommodate, 1 is better than minus 1. But these are two deviations. The entrant has to deviate from out to in and send the incumbent from fight to accommodate. And what we rule out in a Nash equilibrium is only unilateral deviations, one deviation. So in the out fight Nash equilibrium, can any of the two players deviate? Unilateral. The entrant can only choose in instead of out. If he unilaterally deviates while the incumbent chooses fight, the entrant gets a minus 3 instead of a 0. So the entrant will not deviate from out to in because he loses. The incumbent chooses fight. What's the payoff for the incumbent? 2, because the entrant chooses out. If the incumbent instead of fighting accommodates, what's the payoff for the incumbent? 2, because the entrant chooses no profitable deviation on the part of the incumbent either. Okay? No players are profitable deviation, both of setmark, out, fight if in, accommodate if in, both are Nash equilibrium. Out, fight tells the incumbent to choose something suboptimal if the entrant enters, and what we will impose here is sequential rationality. So if we impose sequential rationality additionally, because we don't like this out fight in mesh equilibrium, then we can eliminate this. And then we solve the game by backwards induction, which will be the subgame perfect equilibrium. Here we get that the incumbent will accommodate, 1 is better than -1, and then the entrant chooses A. So subgame perfect equilibrium, backward induction, sequential rationality require to solve the game from the end. Every player at each decision node, also the ones which are not occurring in equilibrium, have to have optimal decision. You have to choose optimally even on decision nodes which do not occur in equilibrium. And based on this, you can anticipate what players will do. And so the entrant anticipates that if he enters, the incumbent will accommodate, and thus the entrant will choose to enter, and we select the Nash equilibrium, which is also a subgame perfect equilibrium, which is in and accommodate, and this is the only subgame perfect equilibrium. Okay. Now, I think let's stop here, because it's 12:30, and we'll do the other one. This is another game with imperfect information, and this is also the last one we do. So this I will do next week on Friday. So next week on Friday we will finish this chapter, there are a couple of slides left, and we'll do the second part of game theory, and then we are done. You please hand in the problems at 3 next week on Friday. And afterwards, since we are done with the course, I'm available for office hours. But until the 26th, we can meet in person. And then again from the 9th on, after all the holidays. So from the 27th till the 9th or 8th, or the weekend before, so the 3rd, 4th, 5th, we can talk online, by email, by Zoom, or by Meet. And before and after, we can meet in the office. But anyway, we have the question session on the 9th, and 10th and 11th we have office hours. We can get some. Good. So see you next week. And you see I'm going faster, but I don't know if it's better to go. It's good. Good speed.
So the progress is already on.
Progress of 3 is already since last week, and now I also know the solution for problem 2.